place where cats can be alive and dead at the same time, particles teleport, and the universe might just be playing the ultimate game of choose your own adventure. That's what quantum mechanics is, and that's where we're going today. Now you might be thinking, quantum what-anics? Don't worry, we're going to break it down faster than a subatomic particle in a particle accelerator. Quantum mechanics is like the rebellious teenager of the physics world. It's the theory that describes how things work at the tiniest scales of reality. And let me tell you, it's got some serious attitude. So, enough cheap talk. Here are 5 interesting things about quantum mechanics. Let's kick off our interesting things list with the wave particle duality. Imagine you're at a beach, right? You see waves in the ocean and you can pick up individual grains of sand. Waves and particles, two completely different things, right? Well, in the quantum world, they're like that dress that broke the internet, both at the same time. Picture this. You've got an electron, tiny little thing, supposed to be a particle, like a really small marble. But then you try to measure where it is, and suddenly it starts acting like a wave, spreading out and interfering with itself. It's like you tried to catch a baseball, but when you opened your glove, you found an ocean wave instead. This isn't just some theoretical mumbo-jumbo either. Scientists have actually seen this happen in experiments. They shoot electrons at a screen with 2 slits in it, and instead of seeing 2 neat lines where the electrons hit, they get an interference pattern. Exactly what you'd expect if you were dealing with waves. But remember, these are supposed to be particles. It's like the electrons are saying, you can't put me in a box, or maybe you can. Who knows? Now let's crank up the weirdness to 11 and talk about the next item on our list, quantum superposition. This is where things get really trippy. In the quantum world, things don't just exist in one state. They exist in all possible states at once, until we measure them. It's like Schrodinger's cat, but instead of just being alive or dead, the cat is also simultaneously making biscuits, speeding around in zoomies, reading War and Peace, and plotting world domination. Speaking of Schrodinger's cat, let's unpack that furball of a thought experiment. Erwin Schrödinger, a physicist with a flair for the dramatic, came up with this idea to show how bonkers quantum superposition is. Here's the deal. You've got a cat in a box. Don't worry, it's just a thought experiment. No actual cats were harmed. In the box, there's also a vial of poison that will break if a radioactive atom decays. The decay is a quantum event, which means until we open the box and look, the atom has both decayed and not decayed. So what does this mean for our feline friend? According to quantum mechanics, until we open that box, the cat is both alive and dead at the same time. It exists in a superposition of states. It's only when we open the box and observe the cat that the superposition collapses and the cat becomes either definitively alive and probably very angry, or definitively dead, and well, still probably very angry if there is an afterlife for cats. Now I know what you're thinking. Come on, that's ridiculous. A cat can't be alive and dead at the same time. And you're right. In our everyday world, that's absurd. But that's the whole point. Quantum mechanics shows us that the rules that govern the tiniest scales of reality are fundamentally different from the rules we're used to in our macro world. Coming up at number 3, let's talk about quantum tunneling. Imagine you're trying to push a bowling ball up a hill. You don't quite have enough energy to get over the top, so it rolls back down. Simple, right? Well, in the quantum world, sometimes that bowling ball will just appear on the other side of the hill, even though it didn't have enough energy to get over the top. It's like it dug a tunnel through the hill, hence the name quantum tunneling. This isn't just a weird quirk of quantum mechanics. It's actually crucial to how our universe works. Quantum tunneling is what allows nuclear fusion to happen in stars, including our sun. Without it, the sun wouldn't shine, and we wouldn't be here. Next time you're out and about on a beautiful sunny day, don't forget to give a shout out to quantum tunneling for making it all happen. Now let's zoom out for a second and think about what all this means. We've got particles that are also waves, cats that are simultaneously alive and dead, and bowling balls that can magically appear on the other side of hills. It's like reality itself is playing a cosmic game of whose line is it anyway, where everything's made up and the points don't matter. But here's the catch. As weird and counterintuitive as quantum mechanics is, it works. It makes predictions that have been confirmed by experiments time and time again. It's the foundation of modern electronics. Without quantum mechanics, we wouldn't have smartphones, computers, or any of the technology we rely on every day. The next time someone tells you that reality is straightforward and makes perfect sense, you can smile knowingly and think about the quantum world, because down at the smallest scales, the universe is a place of infinite possibilities, where the lines between particle and wave blur, where cats can be alive and dead, and where the very fabric of reality is far stranger and more wonderful than we ever imagined. And hey, if all of this quantum weirdness is making your head spin, don't worry. As the great physicist Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. So welcome to the club. We're all confused together, and isn't that the most quantum thing of all? What's the one thing you like the best about quantum mechanics? Leave a comment below and let's talk about that amazing thing. If you thought wave particle duality and Schrodinger's cat were mind-bending, wait until you hear about item number 4 in the list: quantum entanglement. It's so bizarre that even Einstein called it spooky action at a distance. And let me tell you, when Einstein thinks something is spooky, you know you're in for a wild ride. So what's the deal with quantum entanglement? Imagine you and your best friend each have a magic coin. When you flip your coin, it randomly lands on heads or tails. But here's the kicker. The moment you see your result, you instantly know what your friend's coin shows, even if they're on the other side of the galaxy. That's entanglement in a nutshell. In the quantum world, particles can become entangled in such a way that the state of one particle is directly related to the state of another, no matter how far apart they are. It's like they're cosmically linked by some invisible thread. The moment you measure one particle, you instantly know the state of its entangled partner. Now you might be thinking, big deal, so they're connected. What's so spooky about that? Well, don't ask for freaky if you won't be able to handle it. According to Einstein's theory of relativity, nothing can travel faster than the speed of light. But with entanglement, it seems like information is being transmitted instantaneously across any distance. Scientists have actually tested this. They've separated entangled particles by kilometers and found that measuring one instantly affects the other. It's not just fast communication, it's instant. No time delay, nada, zip. Can you imagine Einstein rolling over his grave? Last but definitely not least in our list, let's talk about the observer effect. No, I'm not talking about how your cat acts differently when you're watching, although that's pretty mysterious too. In quantum mechanics, the act of observing something actually changes it. It's like reality is shy and doesn't fully commit to a state until someone's watching. Here's how it works. Remember our friend, the electron that was behaving like a wave? Well, if you try to measure which slit it goes through in that double slit experiment, suddenly it starts behaving like a particle again. It's like the electron knows it's being watched and decides to play it cool. Wave? What wave? I'm just a regular old particle. Nothing to see here. This observer effect leads us to one of the most famous and controversial interpretations of quantum mechanics: the Copenhagen interpretation. This idea, cooked up by physicist Niels Bohr and his buddies in Copenhagen, hence the name, suggests that a quantum system remains in a superposition of all possible states until it's observed. It's only when we measure it that the system collapses into a definite state. If this is making your brain hurt, you're not alone. Even Bohr himself once said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." So if you're feeling a bit shocked and confused, congratulations, you're on the right track. Now, let's take this to its logical or illogical conclusion. If observation collapses the wave function and determines reality, does that mean nothing is real until it's observed? Are we all just walking around in a giant quantum superposition until someone looks at us? It's like the old philosophical question: if a tree falls in a forest and no one is around to hear it, does it make a sound? In the quantum world, the answer might be the tree is in a superposition of fallen and not fallen until someone observes it. This idea has led some people to make some pretty wild claims. Some have suggested that consciousness itself might play a role in collapsing the wave function and determining reality. It's like we're all secretly reality-bending wizards, shaping the universe with our minds. Cool idea for a sci-fi novel, but most physicists aren't quite ready to go that far. Speaking of wild ideas, let's talk about quantum Zeno effect. Named after the ancient Greek philosopher Zeno, who had some pretty trippy ideas of his own, this effect suggests that an unstable particle, if observed continuously, will never decay. It's like the quantum version of the "a watched pot never boils" saying, except it actually works. Experiments have shown that rapidly repeated measurements can slow down quantum processes. It's as if by constantly checking on a system, we're freezing it in place. Imagine you could keep your ice cream from melting just by staring at it really intensely. That's kind of what's happening here, but on a quantum scale. Now, if all this talk about observation and measurement is making you feel a bit paranoid, don't worry. You don't need to be a conscious human observer with a lab coat and clipboard to cause wave function collapse. Any interaction with the environment that could potentially reveal information about the quantum system counts as a measurement. So you can relax. The universe isn't depending on you to keep it real. But this does raise some pretty mind-bending questions about the nature of reality. If quantum systems can exist in multiple states simultaneously until they're measured, what does that mean for our understanding of cause and effect, of past and future, of free will? Some physicists have suggested that maybe the wave function never actually collapses. Instead, every possible outcome happens, each in its own separate universe. This is the many worlds interpretation, and it's exactly as bonkers as it sounds. According to this idea, every time a quantum event occurs, the universe splits into multiple versions, one for each possible outcome. It's like reality is a choose-your-own-adventure book, and every choice spawns a new universe. If this is true, there are an infinite number of universes out there. There's a universe where you had cereal for breakfast this morning, and another where you had toast. There's a universe where you're watching this video, and another where you decided to watch cat videos instead. No judgment. There might even be a universe where you understand quantum mechanics perfectly, but I wouldn't bet on it. The many worlds interpretation solves some problems with quantum mechanics, but it creates others. For one thing, if every possible outcome happens, what determines which universe we find ourselves in? And if all the possibilities are realized, does that mean nothing we do really matters, since all other choices are being made in other universes anyway? These are heavy questions, and they show how quantum mechanics isn't just about tiny particles and abstract math. It has profound implications for our understanding of reality, consciousness, and even the meaning of existence itself. It challenges our most basic assumptions about how the world works and forces us to reconsider what we think we know about the nature of reality. So next time someone tells you that science has everything figured out, just smile and think about quantum entanglement, the observer effect, and the many worlds interpretation. Because the truth is, the more we learn about the universe, the stranger and more mysterious it becomes. And isn't that exciting? We're not at the end of discovery. We're just at the beginning. The quantum world is out there, weird and wonderful, just waiting for us to unravel its mysteries. And who knows, maybe in one of those infinite universes, we already have. And hey, if you enjoyed this mind-bending journey through the quantum world, don't forget to smash that like button and subscribe to the channel. Who knows what quantum weirdness we'll dive into next time. Until then, stay insanely curious, stay quantum, and remember, you're a walking, talking quantum miracle.